So today we're going to discuss about matrix factorization. So what is matrix factorization? Uh, okay, so these are some of the references, very relevant. This is not a very old approach, as you can see. In 1999, the first work it came out in Nature, and subsequently the optimization techniques or the algorithms were published in NIPS conference. So, okay. In the last class, we had seen PCA, and PCA is a kind of, we saw how a PCA can also be interpreted as a kind of matrix factorization. So let's see what is matrix factorization. Can you see some pattern in this matrix? Can you see some pattern in this matrix? So all of machine learning is pattern search, right? Finding patterns in data. Can you see some pattern in this representation with the goal that you want to compress the data size? Few columns are repeating. So you have the first column, third column, and sixth column. They are same. And the second column is 0, last column is also 0, and then similarly the other three are also same. So basically, there are only two columns which are repeating. Can I write it like this? Here I can say this column. So if you multiply these two matrices, this column gets multiplied with the top row, the second column gets multiplied with the second row. So let's see the first entry. The top row is 0, so 0 gets multiplied with this whole column, so you get nothing. And 1 gets multiplied with this column, both are added, and you get the first column only, right? So this is controlling. So these two entries are controlling how do the two columns will add, right? So these two columns will add based on these entries. So here it says just take the second column, first column is 0, and that's what you get here. Then the next one says both columns are 0, means don't take any of them, and that's what you get. You don't get any of them here. This one says, okay, the second column should be taken. That's what you have taken on third column here. The fourth entry says that you take the first column, not the second. Is it clear? If this is clear, then you have understood half the class. Okay, so how we represent it? We say this is my V. V is the original data matrix. And I want to decompose it into two matrices. One is W, which is the dictionary. Dictionary means the actual entries which are there. So W means the dictionary. The dictionary entries are the actual entries which are there in our data, the columns of the data, and then H are the activations. Activations means which entries are getting activated at which time instance. Okay, you can consider this is your time or different samples, and this is single data point, single sample, right? And these are and this is controlling how at different times which columns are adding up. Okay, so be very clear about this representation. Should we go forward? Anybody has any question, please ask. Okay. Okay, so what is the advantage? First is reduction in size, that you are able to reduce your size. V was m cross n, let us say. So the data size is m into n, right? M into n. And if you break it down into two matrices W and H, and W is of size m cross R, where R is taken such that it is small, right? Then similarly, H is R cross N. So in this case, R is 2 here, right? And then if R is small, then so what is the total size in the right hand side in the WH representation? Total data size is M into R plus the size of this, which is N into R, right? Or R into N. So M into R plus R into N should be smaller than M into N. If that happens, then you get a significant reduction in the data size, right? And then what, okay, this is the reduction. So basically if you want to transmit information, you can do it very efficiently with less amount of bits needed to for communication. Next, it is very useful for analysis. Can anybody tell an analogy? How is this useful for analysis? How is it useful for analysis? To remind you, we studied some clustering techniques. Clustering techniques. Can this be compared to a clustering technique which is trying to find efficient clusters in the data? Like those patterns which are similar, they are clustered together, and your dictionary elements are the mean points, the center points, right? Okay, so this is useful for analysis. You can do dimension reduction, but you can also do classification, and you can find nice patterns in the data. Another very important advantage here is it is useful for reconstruction. You cannot use linear classifiers for reconstruction, can you? Reconstruction means if I give you the classifier and I ask you, can you reconstruct the samples which will satisfy this classifier, right? But in this case, you can do that. This is a major advantage of matrix factorization techniques, that you can regenerate the data which the model represents. So this is very useful for reconstruction. Okay, so let us discuss different, so this was a simple example without any noise, with like very clean pattern. You can clearly see there are just two data types which are appearing again and again, but in real life situation you have got noise. Let us say in this case, we have got noise. What is the noise here? So, I have added a Gaussian noise to my V, right? But still the pattern is same, right? You can see here the values are decreasing from almost like 1 to 0. Here the values are increasing from, no, they are almost 0. All of them are almost 0. Here the values are decreasing from 1 to 0. Here they are increasing from 0 to some large value. Increasing from 0 to some large value. Then again decreasing. So if you do a k-means clustering on this data, right? You have got how many? 8 samples. And if you do k-means clustering with 2 cluster centers, so, and then you represent each data point. Let me show it pictorially to make more sense. Let us say you have got 8 data points, something like this. This is in higher dimension. I'm showing it in 2 dimensions just to simplify your visualization. Let us say I take this as my one data center, this as my one data center, and I represent each point with the data center only. If you ask, let us say this is my point x1, this is x2, vector, these are vectors, x3, and let's say this is x5, and this point is mu1, and this point is mu2, and I say replace all x with mu1, x2 also becomes mu1, but x5 becomes mu2, right? You are replacing the data points with these, mu2, you are replacing the data points with these cluster centers. So that is one form of matrix factorization. What is the constraint? The constraint becomes, okay, when you do, okay, let's see here. When you do W into H, this is my W, this is my H. So my H is a kind of delta function, right? Means it is 1 for one entry but 0 for all others. right? So this is called k-means clustering, which you use for vector quantization. You're quantizing your data. You have studied quantization for signal processing also, right? In DSP you studied quantization. Something very similar. There it was one-dimensional quantization, here it is multi-dimensional quantization. That is why it is called vector quantization. Okay. So this is an example of vector quantization applied on images. So don't be confused by the image being of size n cross n something. So represent one image like one vector. Can you please close the door? Thank you. So represent each image by a vector, as a vector. So let us say this is the original image V, and this image is of size m cross 1, right? I put everything in terms of one column vector, right? M cross 1. And I want to, and in this way I have got so many images, like 1000 images, right? And I want to apply vector quantization, then how will it look like? So you are basically finding good clusters. Let's say all people with moustache are clustered together, all girls with long hair are clustered together, all men with bald hair or no hair, they are clustered together. So in this way, we get clusters, right? So this will learn, so vector quantization will learn those representations. But the constraint is that at a time, only single cluster or only a single center will be activated, right? So if this was my input image, and this is a dictionary which I have learned from 1000 images, right? This is I have learned this from 1000 samples or 1000 images, and this is my single test image, test sample, which I want to represent in terms of vector quantization. Then at a time single entry is active, so this maybe it looks like this entry is active, right? And then you get this. So basically this image will be approximated by this image, which is okay, a good enough approximation, although not very perfect. Does that make sense? Okay. Next, there is another technique of matrix factorization which we saw in the last class, which is PCA, principal component analysis. So how can this be interpreted as matrix factorization? So basically you get Y as a combination of U and X. What is U here? U are the eigenvectors, right? U are the eigenvectors of, I've written actually here. So U are the eigenvectors of S, which is the covariance matrix of the data normalized, zero mean samples. Okay, so this is a way of matrix factorization. Here Y, U and X, okay, this Y, this U and X, they can take any real values, right? They can be positive, negative, whatever. But for images, negative values do not make sense. Let us say you are reconstructing your given image and you are getting negative values. What will you do? What will you do? You can simply clip them. Okay, make all the negative values clip to 0. But still, that is not the best solution, right? Because it's a kind of you're hard forcing. It's not coming out as a principled approach. It is just a kind of hack. Then you have, but for images, negative values do not make sense. Can we constrain U to have only non-negative values, and so that my Y will also be non-negative? Basically, I want to constrain my U and X and Y, all of them to be non-negative. Y is anyways non-negative for images and for so many other cases, especially for images, the one which we have seen. I'll discuss more examples a little later. So in this way, PCA cannot be used for non-negative constraints, right? But it can be used as where negative values are allowed. So how do you interpret PCA as matrix factorization? So just as you do dimensionality reduction, So those dimensions along which you are reducing your dimensionality, that becomes your basis, your dictionary, and your activations are the weights which are used to reconstruct. So here, so U is your basis, right? So U, this is your dictionary, and these are your activations. But the activations can be negative also, they're not just positive. And even dictionary also can have negative values. Another thing is, all your dictionary entries are, all dictionary entries are orthogonal or orthonormal, because their norm is also 1. Okay, so in this way, you can use PCA for matrix factorization. So here is an example. Same example, the V, this is your image, the input image, and this is the dictionary which you have learned from 1,000, let's say, training data, 1,000 different images. And this is the activation which you get for this particular image. So basically it says, okay, so red values are the negative values. So you can see positive and negative everything. And finally you clip out the negative values and this is what you get, which is certainly much better than your VQA representation, right? Because VQA was a hard mapping, but this is a soft mapping where you take different components from different images, add them up linearly and construct the whole face, right? So this was PCA. Now let's come to the next example, which is non-negative matrix factorization. So basically, if you want to put these constraints that my data V is non-negative, non-negative means it can be either positive or 0, but it cannot be negative, right? So non-negative matrix factorization. So I'm constraining my V to be greater than 0, W to be greater than 0 or equal to 0, H to be greater than equal to 0. Right? This is the meaning of non-negative matrix factorization. Where is it useful? It is useful in case of images. As you just saw, images can have values between 0 to 255, which you normalize to, let's say, 0 to 1. Right? So images are non-negative. And then spectral magnitudes. If you work with audio, you have already seen, you have worked with audio, you have worked with time series, you have worked with different signals. So if you take their spectra, they are complex numbers. But if you take their magnitudes, they are positive or non-negative, right? So spectral magnitudes are non-negative. Then energies are positive or non-negative. Similarly, counts. In natural language processing, you often use counts as a measure of, as a feature of your data. Let's say if you have a document. In that document, what is the different counts of different keywords or different important words, right? Based on that, you can classify the document, you can process the document, like email spam clustering. So you look for some keywords or some groups of words and you count their frequencies. So counts are non-negative. So it is very useful to have non-negative dictionary and activations. Why? Because it gives interpretability as well as dexterity. What is interpretability? I will show you this example in PCA. Can you interpret what it represents? What these eigenvectors represent? So these eigenvectors or eigenimages, what do they represent? It's very hard to know. It looks like some like uninterpretable thing. But I will show you examples. Okay, here is the example. So this is an example of non-negative matrix factorization. So you can see that the W dictionary is all positive, 0 or positive, non-negative. And you can see that different components of the dictionary, which are different blocks, they are learning different parts of the face. Like this is learning some eyes and the mouth. This one is learning the right side of the face and some eye. This one is learning somewhere around the forehead. This one is learning the eyes. Means this has some better interpretability, and because of which you also get better dexterity. We'll discuss that point a little later when we go to some applications of this. Okay, and similarly, the activations are also positive. So it says, okay, take the eyes from here, take the nose from here, take the ears from here, and reconstruct the image. Right? That makes much more sense. That is much more interpretable. So generally, I have seen like in the movies, when detector movies, so somebody remembers vaguely some face. Sometimes artists are not there, so they have all these bits and pieces. The artist will ask, okay, does the eye looks like this? Do the ear look like this? So in this way, they try to reconstruct the whole face using small parts, right? Something like that. So these parts are learned automatically, not designed by any artist, but they are statistically learned from the data. Okay, so this is the meaning of interpretability, and it gives much more dexterity. And the dictionary is learning different parts which are interpretable. Okay. Another example, you can see from MNIST data, which is the digits data, different handwritten digits. We discussed this data last time in the last class. So the basis components are these different images, and these are the mixture weights. For this as the input, I get these activations. For this as the input, I get these activations. So you can see you can construct so many different varieties of images using this method. And these things are interpretable. Okay, this is a curve, this is a different kind of a stroke, this is a different kind of a stroke. Okay. Now question is, okay, how do we do NMF? How do we do non-negative matrix factorization? So in this case, V is known, right? I know V, but W and H are unknowns. I do not know my W matrix and H matrix. So how do we do that? So simple solution is you do them turn by turn. Given V, initialize W, then estimate H using the using the W which we have assumed. Then with that optimal H, keep it as fixed. Update your W, and then fix your W, update your H, fix your H, update your W. In this way, you keep iterating until you converge, right? That's how you do. That's how you saw in ML estimation, maximum likelihood estimation for certain things like which one? GMMs, Gaussian mixture models, right? Not the Gaussian, but Gaussian mixture models, right? So that's what you did in EM algorithm. Okay, so let's discuss about parameter estimation in case of NMF. So any parameter estimation, the first thing you do, what do you do? The first thing. What is the first thing you do to estimate your parameters? Random initialization, no. The very first, very essential thing which you do to find your optimal weights. Metric, yeah. Define a metric. Form a space. Form a metric in which you want to minimize or maximize, so that you can estimate your parameters, right? To estimate your parameters, you need a loss function or an objective function. That is the first thing you do, and you have to do it. Machine won't do it automatically. We have not yet designed a machine which can determine automatically its loss function or objective function. So that's what we do here. So what is most obvious metric in this case? Squared loss function. This is not the only thing. This is not the only loss function. You have seen so many other kinds of loss functions, especially for positive terms. What is the loss function which you have seen when all entries are positive? Huh? What? Categorical cross entropy is valid only if you have delta. One of them is delta, but here we don't have delta. Scale divergence, yes, scale divergence. So you can use scale divergence by first you have to normalize them, and then you can use KL divergence. So right answer, we'll see KL divergence very soon. So this is the simplest loss function, just squared error loss function or mean squared error loss function. So what is the constraint? The constraint is that W should be greater than or equal to 0, H should be greater than or equal to 0. These are your trainable parameters, and V is fixed, right? And then you can also write it in terms of element wise. So this was matrix wise, this is element wise. V is a matrix Ij, Vij. So WIR into HRJ, and you sum over all R, which is like a matrix or vector multiplication. That's it, simple loss function. Okay, how do you optimize this loss function now? What are the different ways which you can use to optimize your loss function? Tell me. What are the different ways to optimize? Huh? Huh? Analytical solution. How do you find analytical solution? Yes, very good. Dou E upon dou whatever, let's say W or H equal to 0 plus the constraints. Okay, you have to put the constraint. How will you put the constraints here? Lagrange multiplier, does it take care of non-negative constraint? Can the Lagrange multiplier take care of non-negative constraint? I don't know, I have never seen, so I can't comment on that, right? This is one method, but I don't know how to put constraints here. Any other method? So basically you are saying this is your ML estimation or something, right? Okay. What other constraint? What other method you can use? Please speak loudly. I heard some right answer. Gradient descent, yeah. So you can use gradient descent. To optimize this, so basically you take your dou E upon dou W, instead of making it 0, if it is not analytically solvable, then you find a trajectory or update your weights iteratively, and you can you apply non-negative constraints somehow here? How? Yes, whenever anything becomes negative, just clip it to 0. Right? Just clip it to 0. That is it. Okay.
What is the path it is taking for gradient descent? Goes through a negative path and then reaches somewhere.
Yeah, so it cannot enter that region. It has to move along the boundary. And it is possible that you may get many entries 0, sparse matrices, and then optimization may become difficult. That is true. So that is why gradient descent is first of all very slow, and secondly very difficult solution. It's difficult to solve with gradient descent here. Are there any other methods? Any other method you would like to use? Huh? Yeah, maybe you can try with something. Possible. Okay, so there is a nice algorithm given in this paper. These are the original proponents of non-negative matrix factorization. So their method is based on something similar to EM algorithm. You remember in EM algorithm we construct an auxiliary loss function which is easy to optimize, right? So the original loss function is difficult to optimize, but you construct an auxiliary loss function which is easy to optimize, but it is always, let's say if you are maximizing some quantity, it is the lower bound. If you are minimizing something, then it is the upper bound, which means by optimizing there, you are guaranteeing that your actual loss function is also improving, right? So something like that is used by this paper. So this paper is your reading assignment. You can go through it on your own. But if you want, I can discuss as well. So it's not a difficult paper. If you have understood EM algorithm, then this is very easy to understand. Now we come to one kind of NMF which you will find very easy to relate with, because the kind of theory you have already read, it is this method can be derived very easily from there. Okay. So once again, what is my goal? So I have got some V, which is my original matrix, and I want to reconstruct this using W into H and with some significant size reduction. So let us say each column of V is my data sample, right? So each column of V is one sample, and I am extracting some good dictionary components. So basically, all these will form this component, all these will form this component, and all these, a few of these will form this component. Oh, sorry, this component. This one is this one. Okay. So basically, you automatically learn the dictionary components from V, and then you have activations. So whenever this one gets multiplied with this, so which means here, so that's why you get a peak here. The second one multiplies with the second one, so somewhere here you get this one, and then when the third one gets multiplied with the third one here, you get this one. Clear? This is very obvious, right? Okay, so just a repetition. Okay, so can you compare it with something? So we have already compared it with k-means clustering, right? And what is k-means clustering? K-means clustering is a latent variable model, discrete latent variable model. Can we compare this method with a discrete latent variable model so that we can use efficient optimization techniques like EM algorithm, right? So given VFT, I want to approximate it as this into this. So here the notations are a little different. So just because I am following this work, so to be consistent with this work's notations, I have modified the notations here a little bit. So here F is my row, F indexes the rows, and T indexes the time, right? F and T. It's like a spectrogram, right? F and T, immediately you can recognize spectrogram. So let us say these are my features. It could be images or whatever, but okay, let us say F and T. And you want to break it down into F cross Z, Z cross T, where Z is a small number, right? Everything is discrete random variable. Nothing I mean to say Z is a discrete random variable here. Okay. Similarly, F can take discrete values, T can take discrete values. Now we assume that VFT is coming from an underlying distribution PF given T. So something like this. Let us say if you have got a vector like this is your F and this is your VFT. So assume that this is like a histogram. So compare it with a histogram. So very important. So your VFT is like a histogram. Right? And we want to approximate PF given T with PLCA. Basically, you want to break it down into two different components, two different matrices. So, and we are using a latent variable Z, which is a discrete random variable. How can you write? If you just this equation will help you to recall many things. So you have PF given T. This is the underlying distribution, and you introduce a latent variable model, latent variable Z, and you marginalize over Z. You construct a joint distribution P F comma Z given T and marginalize over Z, right? Am I making sense? Please raise your hand if you don't understand anything, right? So you are marginalizing over z, and you can open it up. You can say pz given t, pf given z comma t, right? The joint distribution can be written as a conditional distribution. Now here, something important assumption we are making. This assumption is that my pf given z is independent of t. What does that mean? These are my dictionary elements, right? They do not depend on time. Dictionary elements are constant. Activations control at what time which dictionary element will be activated. Z is the index which is controlling my dictionary element. So it means it is telling which dictionary element it is, right? So pf given z is independent of time. So basically f is independent of time given z, conditional independence. Okay, so this is the assumption. Okay, pft, I have broken it down into pf given c and pz. Okay. Now t is not a random variable here. Okay, let us assume t is not a random variable here. T is a given quantity, right? The sample index. I have got 100 samples. The sample index is a given quantity. So I am not assuming t as a random variable in this case. Only two random variables are there, f and z, right? Now my aim is, given vft, I want to estimate the underlying distribution with the help of latent variables. Analogy, you can assume this is like there are underlying clusters which you are trying to find, right? Or you can assume there are underlying classes which you want to find, or if it is an unsupervised case, then these are different parts which you want to find in the dictionary basis. Okay, and the best solution which I can use is maximum likelihood estimation, right? You did this for Gaussian mixture model as well. You did this for Gaussian models also. Same thing we will do here. So we have PTF, which we want to maximize for the given samples. What are the samples? So if this was my histogram, what are the samples? Samples are the entries which are bringing the histogram up, right? So this is a sample within the sample. You have images or vectors, but you are assuming that these vectors are histograms, and something which is causing this histogram is something more fundamental, which you are calling as f. So a little bit imagination you have to put here to be able to see, okay, there is somebody like shooting bullets and creating these patterns. These are the statistical patterns created by these bullets, and each bullet is your P of f, right? So probability that the bullet will fall at this f, and this is the histogram. Let me write it down so that you remember it. This is like a histogram. Okay, if I say now log likelihood, this will be summation of log PTFI, right? But you know the counts, right? You know the counts. What are the counts? VFT are the counts. Can you write it like this? So what is the difference between Fi and F? Fi are the actual samples, but F is the number line. Remember this. Like we have discussed this point in the past also, right? When you do sample, this was a question in midsem also. Many of you did it right. Some of you also did it wrong. So there's a difference between samples and the number line. Fi are the samples, F is the number line, right? So this is how you convert your equation from samples to the number line by just multiplying with the counts, right? Okay, so now the log likelihood function which I want to optimize is this function, and you know how to do it, right? How you will do it? This is the function. So over all the time you can write it like this, and then you know you have to introduce latent variables z. So you write down PTF as marginalized over z, PT z, and PF given z. Clear? Now what will you do now? There is a summation inside the log. If you try to find an analytical solution, you will be stuck. You won't be able to find it. So what will you do now? EM algorithm. So what is the first step which you will do? What is the first step which you will do to simplify this log likelihood, to construct an auxiliary log likelihood which is easy to optimize? Jensen's inequality. Very good. So this is the Jensen's inequality that you divide it by some QZ. You divide it with some qt z given f, and similarly multiply it with qt z given f. Right? And then you know these qt z given f are the probability distributions. These are PDF, so they are always greater than 0 or equal to 0, and this sum to 1. So you can apply Jensen's inequality and bring out this qt z given f out here, and you say that this term is always greater than. So if you want to maximize your log likelihood, you maximize this lower bound, then you are good to go. And this log likelihood can be analytically maximized. So this is the auxiliary function, right? This thing. And now what will you do? Now what do you do in EM algorithm? You first find the expectation term, which basically means you minimize the distance between the two distributions, if you remember it. So you have got some distribution like this, which you want to maximize. This is the log likelihood. You have got some auxiliary function which is equal here. So first of all, you have to make it equal. To make it equal, you set your you make the KL divergence equal to 0. What is the KL divergence? It is basically the divergence between the numerator and denominator, which means you make qt z given f equal to this thing. Then your KL divergence will become 0. Okay, just to remind you, first you make the KL divergence 0, that is the E step, and then you optimize for theta, that is the M step, which is analytically solvable. Okay, this slide is exactly from your EM algorithms slide. Okay, now what do you do? So in the E step, you set your Q equal to PTZ into PF given Z. You have to normalize it because the numerator is not normalized, so you normalize it over Z, right? And then next, you do the maximization. Maximize the auxiliary loss function with respect to theta. So let us do this step in detail now. So you have got, this is your auxiliary loss function. What is your theta now? What are the unknown quantities? The W and H, right? Both you want to estimate. You don't know the dictionary elements, you don't know the activations. So now what are your dictionary elements? PF given Z are your dictionary elements and PTZ are your activations. So what are the constraints? One constraint is both are non-negative. Are those constraints satisfied here? Yes or no? Why? Because these are probabilities, right? So they are definitely satisfied. But the next constraint, that they should sum to 1, that constraint is not satisfied automatically. That's why we have to introduce Lagrange multipliers. You introduce these terms that PTZ should sum to 1 over Z, PF given Z should summed over F should sum to 1. So you get your Lagrange terms, this one which makes PTZ equal to 1, and this one which makes PF given Z sum to 1. Right? These are your Lagrange terms. Now you know what to do. You will differentiate this auxiliary function with respect to, let's take the first term PTZ. You will do with respect to both one by one. So let's say first fix your PF given Z and differentiate with respect to PTZ. And what is the derivative? BFT. So you have P T dash Z dash, right? So remember that differentiate it with respect to a dashed quantity, then you won't make a mistake. So all T are not appearing, only T dash will appear. Similarly here, this is a function of T and Z, so T dash and Z dash will appear. And this quantity is PTZ. So 1 upon PTZ, that's it, plus this term minus lambda T dash. You make it equal to 0, exactly like you did in GMM case. Now, if you rearrange, it becomes something like this. If you sum over all the Z dash, this term will go to 1, right? If you sum to all Z dash, this term will go to 1, and Z dash will multiply here. Basically, summation over Z dash will appear here, and you will get the value of lambda T dash. And you substitute the value of lambda T dash, and you get your PTZ, which is this thing, right? So what was my PTZ? From here, my PTZ was PT dash Z dash this is equal to summation over f v f t dash times q t dash z dash given f, right, divided by lambda t dash. And you have already found the value of lambda t dash, and you just substitute it back, and you get the numerator is as it is and the lambda's value the same thing summed over z dash, right? Is this clear? Okay, and similarly you can do it for pf given z, same thing. So you have ptz, you have now fixed ptz, and make this as your variable and you optimize for this. It's by symmetry you will get similar form, right? Just from symmetry your f will become z, and sorry, here z will become f and t will become z. Okay, we can solve it again, but this by symmetry you can just turn your z into f and t into z, and you get this, right? Oh, that's it. Okay, so today we have finished 1 minute early. Anybody has any question? Anybody has any question? Yes, we don't take t to be random variable because we exactly know the value of t. You know the sample index, right? In this case, you can make t as a random variable also. It will control. Let's say in this case, I showed one example in the beginning of this. Yes, let's say in this case, here is 0, nothing is appearing, right? But if you say this comes from a pf given t, then it will have to be some pattern. Some means all these entries should sum to 1, right? But it does not happen here because they are all 0. So this one, in this example, the assumption that t is known won't hold. So here you have to define an extra random variable called t, which is controlling the distribution across t, the distribution of your bullets across t also, right? So in this case, t has to be considered as a random variable. Actually, if I show you the trick, so here is the t. Okay, I just had hidden it to not confuse you. Okay, but don't get confused. You will see examples later. Okay. So this figure is taken from a paper on PLCA. It's one of very old works, means basically in 2001 maybe or 2007 probably. But this was a very nice idea, one of the first papers to implement PLCA for audio applications. Okay. Thank you. Now we have exam at 7:30 in NCL. Anybody has any questions or doubts, you can ask. Otherwise, we'll meet in the exam.